Now, when evaluating limit of a quotient, that is evaluating limit of a rational expression as x equals c, if the limit of the numerator exists and it's equal to L, which is not 0, but the limit of the function in the denominator as x approaches c is equal to 0, we say that the limit of the expression does not exist. So if we get something like L over 0, we say that the limit does not exist. So if we get a constant divided by a 0, that means it does not exist. The limit does not exist. And also, if we get the limit of that same expression and both of them are 0, the limit of the numerator is 0, the limit of the denominator is 0, then we say that the limit here is indeterminate. So 0 over 0 is an indeterminate form. That means we can't determine it yet. So that means we need to do something to determine the limit. Now let's consider evaluating the following limits. So previously we learned that when we are to evaluate limit, the first step is to plug in the value of x here into the given expression. Now let's apply that here. Let's evaluate 2 to the numerator. You have 2 squared minus 4 is equal to 0. 2 squared is 4, minus 4 is 0. And then in the denominator, 2 minus 2 is also equal to 0. Now we have 0 over 0, which is indeterminate. So when you get an indeterminate form, that means you cannot determine the limit yet, and you need to do something to evaluate the limit. Now, the first technique that you can do is to try to factor both numerator and denominator and look for common factors. The common factor makes both numerator and denominator equal to 0. So we evaluate this limit by first factoring out the numerator. The numerator can be factored into x minus 2 times x plus 2. And the denominator is x minus 2. Then notice that x minus 2 here is a common factor or a common expression, both numerator and in denominator. And therefore we can cancel this common expression here because this is what is making both our numerator and denominator equal to 0. Then we're able to reduce this into x plus 2. And then that reduced expression is the only expression where we would evaluate the limit. So that means this one, to evaluate the limit here, we reduce it to some expression, x plus 2, and then evaluate the limit at this expression here. And that is equal to 2 plus 2, which is 4. Now also, if you look at the graph of this function and this graph here, you will notice that the graph of this function is equal to the graph of the line y plus 2, but with a hole at x equals 2. Note in general, the value at which both numerator and denominator are equal to 0 would mean that the graph of that function has a hole at that value of x. Now let's consider this example here. Evaluate the limit of x minus 2 over x squared plus 4. The first thing that we need to do is plug in 2 to the expression here. So we have 2 minus 2, that is 0, divided by 2 squared plus 4. We have 0 here, and the denominator is 8. This is 4. 2 squared is 4, plus 4 is 8. 0 over 8 is equal to 0. So as a remark here, in these two examples, if you have 0 over a constant, that means the limit exists and it is equal to 0. If after you plugged in, you get 0 over 0, that means the limit is indeterminate. You don't stop at that point, but you need to do something to get the limit. And the first technique that we learned is to factor both numerator and denominator and find a common factor that makes both numerator and denominator equal to 0, and then cancel that common factor. You're then able to reduce the original expression into an equivalent expression, and then you use that equivalent expression to evaluate your limit. Now let's consider the following limits here and find the limit, and if the limit does not exist, explain why. First step when evaluating a limit is to plug in the value of x here to the given expression. So for letter A, we just plug in x equals 3 to the expression and evaluate. So you have 3 plus 1 divided by 3 plus 3. 3 plus 1 is 4. 3 plus 3 is 6. Simplify this. We have 2/3. Now we get a value. That means the limit is equal to 2/3. Letter B. We do the same thing. You plug in. So you have 3 minus 3. And then the denominator is 3 squared plus 9. You get a 0 in the numerator. The denominator is 3 squared, that's 9, plus 9, 18. 0 over constant is 0. That means that's good. The limit here in this expression is equal to 0. Letter C. You plug in x equals 3 to the expression here. You have 3 squared minus 9 divided by 3 minus 3. What you get here is 3 squared is 9, minus 9 is 0. The denominator is also equal to 0. 3 minus 3 is 0. So we got an indeterminate form. If you get an indeterminate form, you don't stop there, but rather you try to factor both numerator and denominator. In this case, the numerator can be factored as x minus 3 times x plus 3. And then just copy the denominator, x minus 3. Then write the limit, since we have not evaluated the limit yet. And then you cancel common factors. In this case, the common factor is x minus 3. Then we're able to reduce this into x plus 3. And then you evaluate the limit as x approaches 3. In this case, you then plug in 3 here to the x here. So you have 3 plus 3, which is equal to 6. And so the limit of x squared minus 9 over x minus 3 is equal to 6. Now let us consider this next set of examples. Let's evaluate the limit here as x approaches 4. So as a start, you just plug in, replace x here by 4. So you have 4 minus 4 divided by square root of 4 minus 2. Now 4 minus 4 is 0, and the square root of 4 is 2, minus 2, that is also equal to 0. So here we got an indeterminate form. And that would mean that we don't stop here, but rather we find the common factor that is making both numerator and denominator equal to 0. But by inspection and by considering what we have learned so far, it seems that it is hard to factor x minus 4 in the denominator. And also this involves square root. So we will now learn a different technique in solving this type of expression. We call that technique a rationalizing technique. For rationalization or rationalizing technique, we use the difference of two squares formula. If you recall, the difference of two squares formula, a minus b squared, is equal to a minus b times a plus b. Now we use this formula here to remove the square root sign here. We do that by multiplying the expression here by its conjugate. So that means we have x minus 4 over square root of x minus 2 and multiply both numerator and denominator by the conjugate of the denominator. So we have square root of x plus 2. When you say conjugate, it should be the same expression, the same first term, the same second term, but the signs are different. So we have square root of x here. We should have a square root of x here. We have a 2 here and a 2 here, but their signs are different. So if you have a plus here, you multiply that to positive. So square root of x plus 2 is the conjugate of square root of x minus 2. And you multiply the same expression to the numerator as well, such that, so that you're just multiplying the expression, the given expression, by 1. So by doing so, you're able to eliminate the square root, this square root here in the denominator. Because if you multiply a minus b times a plus b, that is the same as a squared minus b squared. So you just square this, or you just square this. You therefore have x in the denominator minus the square of this, which is 4. And that is this expression here in the numerator. So you copy this. So you have x minus 4 times this expression here, which is the square root of x plus 2. And then now you can cancel x minus 4, the common expression that makes both numerator and denominator equal to 0. So therefore, you can now evaluate the limit of the function. So the limit of x minus 4 over square root of x minus 2 as x approaches 4 is the same as finding the limit of the equivalent expression and on all x except at x equals 4, which is square root of x plus 2 as x approaches 4. Now you just plug in the square root of 4 is 2. So you have square root of 4 plus 2. And square root of 4 is 2 plus 2 is 4. So the limit here is equal to 4. Now let's consider finding the limit of the given expression here. The first step is to evaluate the given expression by the value of x here. So you plug in x equals 3 to x here. So you have 3 plus 1, then you take the square root, minus 2, divided by 3 minus 3. The denominator is equal to 0. the numerator, square root of 3 plus 1, that is square root of 4, and square root of 4 is 2. Minus 2 is 0. So we have an indeterminate form here. That means we don't stop there, but rather we either factor or rationalize it. Since this involves square root, therefore we can use the rationalizing technique. That means we will multiply the numerator here, because this is the one that involves square root. We will multiply it by its conjugate. So we have square root of x plus 1 minus 2. You just copy. And then multiply it by the conjugate of the numerator. The conjugate of the numerator is square root of x plus 1 plus 2. You just have to change the sign here to positive. So copy everything and then change the sign to positive. And you multiply the denominator by that same expression. And then the numerator, using this formula, becomes x plus 1. You square each term. You square each term here. X plus 1 minus 4. And then you copy the denominator. You have x minus 3 times the expression here, square root of x plus 1 plus 2. Now you simplify. X plus 1 minus 4 is x minus 3. Copy the denominator. Now, notice that this expression is common to both numerator and denominator. So you can cancel this. That means you're able to reduce this expression into this. So this would mean that the limit here is just equal to the limit of the reduced expression, which is 1. The numerator is just 1 after we canceled x minus 3. So 1 over the remaining expression, square root of x plus 1 plus 2, as x approaches 3. Then you plug in. As x approaches 3, that is 3 plus 1 is 4. So the square root of 4 is 2 plus 2. So 2 plus 2 is 4. So the answer is 1/4. The limit of this, as x approaches 3, is 1/4.